So in the video, we go through Hubble, how we explain, and then how we to get through the cosmological principle of the universe, homogeneous inequalities, tell us to know the frequencies. And it's really important with stars to kind of scale these must outlive of straight first lots of living galaxies, and he found that sort of light redshift is the galaxy from galaxy I mean, galaxy by galaxy move around, that's all other. But when you these universe, these are all moving away from us. They are all the universe to be getting the third day, it appears to be distant galaxy. What he like always do is or he drew a graph. So if you plot it of this between us and that galaxy is on the axis. I mean, those not real, but I've just drawn that line, and it's over here or over there. A good straight going through the origin can say loss of recession speed and distance. That's what Hubble or galaxy is fast. It's going to be obvious. I'm normally quite sure, typically to a second. In seconds. And that's look at this graph. We've seen that the recessional speed is proportional to the distance the star is away from us, and that's what Hubble saw. So remember, Hubble, the observations he made, the further away a galaxy is from us, the bigger the redshift, so the faster it's moving, and most galaxies are moving away from us. So I'm going to move these sheets from underneath. I don't want to ruin the surprise. What's coming up? You can kind of see through. Right, okay. So this is Hubble's law. I'm just going to try and focus this a bit better. There we go. So if you've got a relationship like we saw on the graph where V is proportional to D, so that's a proportional symbol, then we can stick a constant of proportionality in there and say actually there's a number that we can multiply each value of distance by, and it gives us the recessional speed. And that value we call Hubble's constant, and it's the symbol for it is a capital H and a small subscript 0. So this equation is what links recessional speed, so the speed at which galaxies are moving away from us. Remember, galaxies are not stars, and the distance those galaxies are from us. And since this was discovered, written down, astronomers and cosmologists have been trying to get a more and more accurate value for Hubble's constant. It's not an easy thing to measure, but we're getting better and better values for that all the time. And the way you improve on these values is to get more and more measurements of recessional speeds and distances for as many galaxies as you can, and make those values as accurate as you possibly can. So, like we said a minute or so ago, recessional speeds in kilometers per second, distance in megaparsecs, and that leaves us with the Hubble constant in really quite awkward units. So because the Hubble constant, if we rearrange that equation, is going to be h0 is v over d, it's going to be kilometers per second per megaparsec. So it'd be kilometers per second over megaparsecs, which is not a nice unit. And in a little bit, we're going to think about how you would actually convert that into better units. Because if you think about this, megaparsecs and kilometers are both units of distance. So we should be able to get the Hubble constant in units which are just equal to s to the minus 1 if recessional speed is in meters per second and distance is in meters. That's what the units of the Hubble constant would be. So Hubble's law, recessional speed proportional to distance, and we can take it one step further by writing this out as an equation. Okay, we'll come back to that in a sec. We're going to take a slight kind of pause here and think about this principle. And these statements are really important definitions for us to remember and also to understand. So the cosmological principle is the idea that when we come up with these laws of physics, it's not just limited to what goes on Earth. We can apply them anywhere in the universe at any time. So when we say a law of physics, like the conservation of momentum or Newton's first law or something like that, we are kind of implying, we are assuming that those laws are true across the whole universe. So if we're going to send a spaceship to a far-flung corner of space, the same laws of physics apply there as they do here, which is quite a statement to make. But it means our physics is much bigger than it otherwise would have been. And then, sort of connected to that, we make these two assumptions. So because the laws of physics are the same everywhere, then the universe is homogeneous and isotropic. And this homogeneous term means that matter is distributed uniformly all over the whole universe. So this means the density is kind of constant wherever we look in the universe. So the universe is kind of the same everywhere. This only applies over big scales. So if you think about it, where I'm sat at the moment, where you're sat in whatever room you're in, the density in that kind of small area is very different to the density of that same area out in space. So the density can change quite rapidly by quite a large amount. But if we're thinking about big scales, the density of this kind of quadrant of the Milky Way galaxy is about the same as the density of a quadrant in another galaxy. And really, we're thinking about even bigger scales than that, where we're looking at clusters of galaxies or groups of galaxies. This is a very large scale thing. And similarly, if the universe is kind of roughly the same everywhere, then it's going to look the same in all directions. So whichever way you look out to space, you're going to see the same patterns of stars and galaxies, or really I should just say galaxies. And this means we're not looking towards the center of the universe or the edge of the universe. So as far as we know, there is no center and there is no edge. And that becomes a bit trickier when we're thinking about things like the Big Bang. And we'll deal with that later on. So going back, you need to remember and learn these definitions, really important ones. Going back then to Hubble's law and the Hubble constant, this is where it becomes really interesting and really useful. With the Big Bang, if we assume that, or if we take what Hubble saw to be true, that everything is moving away from each other, the universe is expanding, then if we go back in time, everything will be a little bit closer together. When you first started watching this video, everything in space was a little bit closer, and since then it's become more spread out. Keep going back in time, further and further and further. Eventually you reach a point where everything is in the same space. So a galaxy which is a long, long way away from us now, at least the space in which that galaxy exists in now, was next or part of the space which our galaxy is in now. And that means that we can write the Hubble, or rewrite that Hubble's law equation like this. So the age of the universe, the time it's taken for the galaxies to spread apart to where they are now, is equal to 1 over the Hubble constant. Now, if we want to use the Hubble constant, so let's say we've made lots of measurements of stars and galaxies. I've got to stop saying stars, I mean galaxies, so measuring the recessional speeds of galaxies and their distance from us, and we've got an accurate value for the Hubble constant, then doing 1 divided by that Hubble constant will give us the time that the universe has existed for, how long those galaxies have been expanding for. The problem is the units, because that would be an easy sum to do if we just got a value for the Hubble constant, work out the age of the universe, which is just 1 divided by that Hubble constant. But that's going to give us units in, or a time in horrible units. So if we want to work it out in years, the age of the universe that is, we need to convert first of all the Hubble constant into per second. Then we can do 1 divided by that Hubble constant and then turn the seconds into years. So to convert the Hubble constant into proper units, and this I would say is the hardest kind of question we get on this topic. So we start off with the Hubble constant as 67.8 kilometers per second per megaparsec. And the way we do this, you want to break this down into chunks. So first of all, if we turn this value into meters per second per megaparsec, that involves multiplying it by 1,000. So 67.8 times 1,000. And I'm kind of instinctively reaching for my calculator. I know I don't need it for this part, but I'm going to get the calculator anyway. Right, got my calculator. So if I do 67.8 times 1,000, which is 67,800. Now I know I didn't need to use a calculator for that, but I'm afraid I use a calculator for absolutely everything. 67,800, and now the units are meters per second per megaparsec. And what we next need to do is divide it by how many meters are in a megaparsec. So in the formula booklet, you're given a value for 1 parsec. So 1 parsec is 3.1 times 10 to the 16 meters. So if we want to work out how many meters, pause there and I'll go back into this. I'm using the free version of this. There we go, back into that. Sorry about that. So if we're using megaparsecs, 1 megaparsec is equal to 1 million. So that is 1 times 10 to the 6 times by 3.1 times 10 to the 16. And that's the number of meters in 1 million megaparsecs. And we want to divide our 67,800 by that value. So I'm going to write this out. So 67,800 over 10 to the 6 times 3.1 times 10 to the 16. So I've got that in the calculator memory already. I'm going to do 1 times 10 to the 6. I'm not sure whether the calculator likes just numbers like 10 to the 6. 3.1 times 10 to the 16, close brackets. And that gives me a value of 2.19 times 10 to the minus 18 per second. So that's the units of the Hubble constant just in seconds to the minus 1. What we then need to do is work out the age in seconds, and then from there work out the age in years, the number of seconds in a year. So I'm going to slide that sheet up so I can still see that. So the age of the universe in seconds will be 1 over 2.19 times 10 to the minus 18, which will be 1 divided by our answer, which is 4.57 times 10 to the 17 seconds. So that's how old the universe is in seconds. And then we want to turn that into Earth years, because that doesn't mean a great deal, does it? Seconds are hard. Once you get beyond, a few minutes worth of seconds, a few hundred seconds, then it's very hard to judge how long that really is. So to get this into years, you are given the conversion for seconds to years in the formula booklet. But if we go through this in this way for now, 4.57 times 10 to the 17 divided by 60, that gives us a value for the Earth, the universe, is age, 7.62 times 10 to the 15, 15 minutes. Divide that by 60, is 1.27 times 10 to the 14 hours. Divide that by 24. Up there so you can see is 5.29 times 10 to the 12 days. Divide that by 365, gives us 1.45 times 10 to the 10 years. And to put that into nicer numbers, that's going to be 14.5 times 10 to the 9 years, which is 14.5 billion years. And that's not a bad value for the age of the universe. 14 and a bit billion years is what we currently think. So the steps to work out that are, this is a fairly kind of involved calculation. So the difficult bit is to convert the Hubble constant in kilometers per second per megaparsec into per second. And to do that, you times by 1,000 to get it into meters per second per megaparsec, and you divide by 1,000,000 lots of the number of meters in a parsec. That 3.1 times 10 to the 16 is given to you in the formula booklet. Once you've done that conversion, Hubble constant in per second, and then we do 1 divided by that to get the age in seconds, and then we just convert the number of seconds into years. But like I said, that conversion for the number of seconds in a year is in the formula booklet as well. So we could just divide the number of seconds by that conversion to get us into the age in years. Okay, so having watched that, have a go at some of the questions on Google Classroom, and good luck.